somera mu ddiiro lyo ng'ewagiddwa. Maryland High School erisangibwa Entebbe, ssomero ly'abawala n'abalenzi. Tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga, nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne.
She gives you her number, but your pen didn't work and the bus is gone. Get a pen you can rely on. Big Crystal, the long-lasting pen with perfect ink flow.
Wamu ne.
Green Hill Academy has high standards of learning and the teachers are very good. They give you a sense of belonging.
Green Hill has helped me to discover my talent.
The environment is good.
Encouraged us children to be excellent.
Wamu ne.
Combo University, a private chartered university that offers world-class education at all levels, including certificates, diplomas, bachelor's and master's degrees. Our courses include computing and IT, law, journalism, nursing, business administration, education, fashion and design, and many more. Admissions for the August 2020 intake are still open. Will you join us?
Wamu ne.
Kids Kingdom Kindergarten and Daycare. Somero ly'abaana bato. Omuzadde leeta omwana ogenda okola ebibyo. Ebyokuzanyisa by'abaana byonna mu nsi tubirina. Ate ng'abaana we bazannyira wagazi nnyo. Jjukira security enka. Amasomero gonna gali mu kikomera. Abasomesa be tulina bakugu mu baana. Abaana tubaliisa bulungi nnyo munnange. Tulina main campus e Buddo Naggalabi nga bwakayisa Buddo Junior.
Yes, a good morning to all of you, our dear students. I want to welcome you to this lesson today. And I want to take this opportunity today as we start this lesson to appreciate, I request the students to be copying that number as they listen. I want to appreciate my dear mother, my mom, wherever you are. I know you may not be watching this lesson, but I want to take the opportunity to thank her on behalf of all the people that have impacted on me. And to you students over there, I want to tell you that the best gift that you can receive from your parents is the gift of education. As we impact on very many young people, I want to thank the parents over there for some of you, I know you are waking up your children to attend these lessons. And to you, the students, I want to request you to make sure that you take your education work seriously. Take your education work seriously. I also want to remind you that I do have some additional material that you can access online on a Facebook page called Let's Learn From Home. Please be encouraged to visit that page, like it, and you will not regret what you'll get from there. Yes, today we shall be looking at that number to open up our lesson. And I want to assume that you've already copied the question. The source, which is the PD supply, is 6 volts. We have 3 capacitors, C1, which is 2 microfarad, C2 and 3, which are each 0.5 microfarads. And they want us to find the charge that is stored, and then the PD across the capacitors. Find the charge stored. Now, we saw that for capacitors that are arranged like C2 and C3, they are in a parallel setup. And when capacitors are in a parallel setup, their effective is usually given by adding, simply adding. It's given by simply adding. So if we can look at the effective capacitance overall, which I am going to write here. I believe you've finished copying the question. So our effective capacitance for the para arrangement is going to be a half plus a half microfarads. They are in parallel, so we simply add them, and this will give us 1 microfarad. So the overall effective capacitance, when we look at this, their effective is now expected to be in series with this one. And therefore, the overall, which I can call the total capacitance, is going to be obtained. Remember, we talked about using product over sum. Since they are now in series, it's going to be, if I call this C prime, it's going to be C prime times C1 over C1 plus C prime. In other words, we say it is product over sum. So it is 2 times 1 over 2 plus 1. And of course, up should be microfarad squared. So 1 microfarad will cancel. And therefore, our total capacitance effective will become 2/3 of a microfarad. But they are telling us to find the charge. So total charge Q will be obtained by using our Q is CV. V is 6 volts. Q is 2/3. So our total charge will be 2 out of 3 times our voltage. Of course, the capacitance, that micro is that, times our voltage, which is 6. And when we simplify, we shall get our total charge as 4 times 10 to the negative 6 coulombs, or if you want, you write it as 4 microcoulombs. They are telling us to find, in the second case, to find the potential difference. They are telling us to find the potential difference across the capacitors. Since we know that from here, from charge is equal to CV, V is equal to charge over capacitance. V is equal to charge over capacitance. So we using C1, if we use C1, for C1, the PD across, if I let it be V1, V1 will be obtained by getting the total charge divided by the capacitance there. And this capacitance, if I call it C1, the PD across will definitely be equal to the total charge, which is now 4 times 10 to the negative 6. That is the charge, divided by the capacitance there, which is 2 times 10 to the negative 6. And this will give us 2 volts. After getting the 2 volts, as the PD across here, if we were to put a voltmeter, it automatically implies that since these two are in parallel, their PD, if I called it V2, should be the same. And of course, they even have the same charge. So for C2 and C3, the PD across, if I call it V2, can be obtained by getting either we get our V2 now as 6, which is the total supply, and we take away V1, which definitely will give us 6 minus 2, giving us our V2 as 4 volts. Or we get the effective in the parallel setup. The effective in the parallel setup, and we look for the PD across. So if we have called it, if we are using this, the total charge is this, we can alternatively say that V2 is equal to charge, which is the total charge, over the effective capacitance there, which we call C prime. And this would be 4 times 10 to the negative 6 out of the capacity, the effective capacitance there, which is 1 times 10 to the negative 6. This will still give us the 4 volts. This is an alternative method. Yeah, to our dear students, I want to give you 2 minutes to capture the solution for that number. 2 minutes, you capture that solution. The solution, not the question. Capture the solution so that we can prepare to go to the next phase. I am very aware by now that all of you, each of you captured this question, so I can clear it off as I give you time to capture our first solution. In the background, I want you to keep reminding yourself or remembering that the best gift a parent can give their children is education. And the best gift a child can give their parent when they are still students is a very good report. And the other reality, you know, I am one of the teachers that is very talkative only when he's in class. The other reality I want to tell you is that the world is not fair, that all of you will copy this work within the given time limit. We naturally have different abilities, and therefore sometimes when I rub off and some of you have not captured something, it is not intentional, but I want to encourage you to be as swift as possible if you must survive like the rest in this world. We are going to proceed to energy stored in a capacitor. Energy stored in a capacitor. Energy stored in a capacitor. And before I derive the expression for energy, I purposed to share alongside briefly. But I can first get the expression for energy, it doesn't matter. And then we can do the rest later. If a capacitor is connected to a source, I'm going to use 2 diagrams, fit them in this space. That if I have my capacitor and I connect it to a battery source or a source of EMF, this is my capacitor and I connect it there. I want to fit another diagram here. This is a capacitor connected to this. So this is a positive terminal, so that would be the positive plate, and this would be the negative plate. Diagram B, I want to have a battery, which I will put in this format. I want to have a battery here. And then I want to have a capacitor here. And here I can connect a bulb or a lamp. Okay, this is a switch. This is a switch. And I want to be very brief here, to use these 2 circuit diagrams to be very brief. with what I want to explain. Now, at the very beginning, I talked about the application of capacitors by comparison, and I talked about the use of the vibrating grid switch and the ballistic galvanometer. Now, I want to use this to describe briefly the charging process of a capacitor. Those who are interested in looking at the animation could be seen maybe if you go to online. But if this is the battery and our intention is to charge this capacitor, we have 2 points A and B and probably C. That if I slide this switch here to connect these 2 points, then the capacitor is able to charge with the current flowing in that direction, with the current flowing in this direction. The capacitor will be able to charge. The capacitor charges fully, and when the capacitor is fully charged, as the capacitor is charging, the potential difference is increasing. Remember, we said the capacitor stores charge in the form of electrical energy. As the current flows, the capacitor charges. If it is fully charged, the current will stop flowing, and that means these terminals will be having equal but opposite charges. This will have a positive charge, and this will have a negative charge. Ultimately, the electrons will be moving from the positive to the negative plate of the capacitor, and the net charge on the positive plate will be positive, and the net charge on the negative, where the electrons have been deposited, will be negative. Now, when we disconnect after fully charging, when we disconnect this part and we now connect this part, this capacitor will begin discharging again. It will discharge, and the discharge will clearly be indicated by any load that is put in this place here. I've put a bulb, but you could put any other device. If you put a meter, it should be able to deflect to show that there is current flowing or charge. But if you put a bulb, the bulb is expected to light brightly, and the brightness will decrease until it goes to 0. That means the capacitor will now be fully discharged. The intention of sharing this before I derive the energy expression is to basically share 3 important graphs. We saw that capacitance varies, charge varies directly proportional to PD. So if we are to sketch a graph, there are 3 graphs they can ask you to sketch. A graph of charge against PD or the other way around should always give you a direct line or a straight line. Even if it is PD against charge, it would still be the same. PD against charge. Now, for the case of charging and discharging, we use the element of time. For the case of charging, we consider a graph of charge against time. We consider a graph of charge against time, and we look at that as the time passes, the capacitor is charging. So it means if you look at the charging graph, the behavior is going to be, it charges from 0 because the capacitor is at 0 charge, and ultimately it ends at a value over time. As time increases, the charge is increasing. Then the one for discharging is also charge against time. If the total charge acquired, for example, here is Q, at that point, this is charge, but the total charge acquired is Q here. Then if we look at this charging curve, it would be an inverse square graph, that as the time increases, the charge decreases until actually when that charge becomes 0. The corresponding charge here is T0. In other words, on the charge axis, the value of charge is 0. So the capacitor will be fully discharged at that time. They can ask you to sketch. They can ask you to sketch a charge against potential graph, or potential against charge graph. This first graph we talked about would suffice. A charge against time for a capacitor charging, this graph would work. And a discharging graph, that one would work. With that finished, I want to use the other diagram I have not talked about. The other diagram that I have not talked about to basically derive the expression for the work done. And we already know, I've already told you that when a capacitor is directly connected, now, the other bit of discharging, as you can see here, when we connect it to switch B, we are like directly connecting the plates of the capacitor, and that is diagram A. That this plate is connected directly to the other plate. Therefore, if we remove the battery here, then the capacitors will discharge to 0. Now, if we put in the battery of a known PD, we want to charge the capacitors to that PD. So if the charge of the capacitor is initially 0, we want to charge it, to give it a charge small q. But if I may use a graph that we have described very well, a graph of PD against charge. Look at this graph. We have said the charge is 0 at the start, and the charge increases with a direct proportion. Now, if we let at a particular charge Q, the corresponding potential difference B. If we let at a particular charge Q, the corresponding potential difference be V, I will use this V as capital V. Then to find the work done, the work will be done by the force that drives the charge through the circuit. And from work is equal to QV, which we saw sometime here, we say if the charge, for example, was small q here, and this charge increases by a small charge, which I will call delta Q. Delta Q is written like this or like that. If it increases by that to a new value, and ultimately that balances up. If we take a small strip to represent the work that will be done in increasing the charge from Q to Q plus dQ, that means the change in the charge is this one, then the work done will also be a small change in work, and that small change in work will be given by the potential times the small change in charge. The potential times the small change in charge. Now, if I want to use, I'm going to use two methods quickly. That since we know that charge is given by CV, if I use this to get the work done, we need to get the work done in charging a capacitor from 0 to Q using a PDV will be obtained in the first case by getting the area. The work done, which we shall consider as the energy, will be the area of the whole triangle here, which is a half base height. And the area will be, this triangle gives us a base of Q and gives us a height of V. This height is V. So we shall have the energy given by a half QV. That is one expression which is very fast. But if we use calculus, I will use this, that if we are charging this capacitor from 0 to Q, it means that the work done will be getting by the integral from 0 to the maximum charge of V dQ. But from here, our V can be obtained as charge over capacitance. So this is case 1. Now what I am pushing from here is case 2. That if I proceed and look at what I want to get, if I integrate, I will get the work done as the integral. If I substitute for V with the charge over C, I'll get the integral of Q over C dQ. from 0 to Q. Because the capacitor, remember, we are saying is charged from no charge to a maximum charge of Q. And if we do the integration, which I know all of you know, I can pull out this 1 out of C and integrate from 0 to Q of Q dq. And that means that my work done will be equal to 1 out of C times, if we integrate this, we increase the power by 1. There is a power of 1. So we shall get Q squared, or Q1 plus 1, over 1 plus 1, which you can write as 2. Since we have limits of 0 to charge, I can say that the work done will ultimately be given by a half, this a half, C times Q squared. If I can change it to this, we can say this is the expression. But now I can remove this part and finalize that. We are moving from right to left. So I can say that our work is a half Q squared over C. And we can say, but Q is equal to CV. Q is equal to CV. So this expression can also be written as 1 out of 2C times Q squared. That is C squared, V squared. 1C can go with this one, giving us work as a half C V squared. So in summary, we can say, or in general, we can say that the energy stored by a capacitor, or the work done, is a half QV, which I got here with you in attendance. But we are seeing that that one can also be the same as a half Q squared out of C. And we have also seen, which is that one, that can be a half C V squared. We can get these expressions, and I will give you yet another few minutes for you to capture this information before we can proceed to look at our next part. As I always tell you, I want to tell you that hard work breaks no bone. But if you're a science student in high school, I can assure you that the only shortcut to excellency is hard work, focus, and determination. Hard work, focus, determination. Of course, you merge it with discussions, consultations, but most importantly, you must be able to practice what the teachers give you. These things are supposed to be easy, and they are indeed easy. Sometimes when you see teachers doing these things here, and they appear to be easy, some of you console yourselves and say they have taught them over a long time. But those of my colleagues out there, I know there are very many teachers and parents that attend this lesson, can actually assure you that these things, we last studied them in A level. At the university, we don't study these things. We only study other hard things that make us more able to be able to deliver this when we fall back as teachers. I want to assume that we have finished capturing this. You know, time runs very fast, and I'm always one of those teachers that come to class with a target. However, my target should not fall short of my learners from understanding. I always want to cover a particular area within the lesson, but I do not cover it alongside the disadvantage of my students. I want to cover it, and I want my students to understand. And I always believe that if I teach you and you find challenges of understanding, it may be very hard for you to understand with even another teacher. That does not mean that I'm the best, but I try to do my best to explain so that if you are attentive, you understand. So we are saying you can use any of these three expressions to calculate energy, and I want us to move to the next stage, my dear students. I want us to move to the next stage. They can ask you to derive the expression for energy stored in a capacitor. They can ask you to sketch the graphs. I've talked about 3 different graphs. A charge against time graph for a charging capacitor. They can be put on one graph, by the way. Charging and discharging can be superimposed on one graph. You saw that they are all charge against time. They can ask you to sketch a PD against charge or a charge against PD graph, which is actually still over there, the one we have used to calculate the area. And if they ask you to derive the expression for energy, you are not under any restriction to actually find a challenge. Yes, I want to now take you to the screen. On your TVs, you must be seeing a question there. Quickly capture that question. And I told you the easiest way to capture the question is for you to take a picture. My dear producer, I would like to request that before I even start solving this number, you can give them the next question and the next one so that they just take pictures and then you go back to that number. You can give them the next question so that you give them all the slides. They take pictures. My dear learners over there, please take pictures of those questions. Don't copy them. I want you to have them so that even at the end of the lesson you have the exercise that I intend to. Take the pictures of those numbers. Yes, there is an exercise. That is an exercise. And even if we don't go through the other numbers I've highlighted as examples, all of them, you should have capacity to do the ones that you have left and the exercise as well. Take the pictures. I think there will be one more slide and then we can get going. Yeah, there's one more slide. That one and another one. Now, I have indicated there that since 2013, UNEB resolved to have 4 sections of this paper. And you will notice that the years before 2013 had sections A, B, and C only. And these questions we are doing used to appear in section C. Can we go back to our the first slide? The first slide. Let us go back to the first slide and we work through the first number. Yes, my dear learners, we are now looking at that number there. We have a capacitor of capacitance C1 given with 2 microfarad. And this capacitor is charged to a PD of 50. If I am to sketch this, I will connect it to a PD of 50 volts. The sketch may not really be very important, but they are asking me to find the charge on each capacitor. For this case, if I call this charge C1, charge is C1V. And we have said that charge is given by capacitance times voltage. So it will be 2 times 10 to the negative 6 times the voltage of 50. And therefore, the charge for this capacitor will be 100 microcoulombs. I request, as usual, that you don't copy while I'm explaining and try to copy after. They have also told us that another capacitor of capacitance, this is also connected to 100 volts. So there is another capacitor. Its capacitance is 3 microfarads. Like I'm saying, you are not under any obligation to sketch, but I'm simply showing you this for purposes of emphasis, that they can give you a question and you also sketch. The charge they want here, which if I can call it Q2 because they are telling us find the charge on each capacitor, will be given by the capacitance times the PD. And in this case, this charge is going to be equal to 3 times 10 to the negative 6 times 100. And this will give us 300 microcoulombs. Part 1 of this question is now done. I called this example 2 because if you realize before the energy I did one example. So that's why I called this example 2. And there we are. We have finished getting these charges. The second case, I want us to move to the second case. This is the core example of this lesson. I want us to move to the second case. And the second case is telling us to find. No, excuse me, we are still on that number. Yes, thank you. If the capacitors are now joined with the plates of like charges connected together, find the charge again. They are saying if they are now joined with the plates of like charges connected together, find the charges again. And then they also want us to find the loss in energy. They also want us to find the loss in energy. Now, before I go to find the charges, let me find the energy here so that we move systematically. The energy stored, I'll call it, I'll combine it. Energy stored, we have just derived the expressions. Fortunately, they are still here. Since I have capacitance and PD, I will use this last one. The energy stored is given by the total energy by a half C1 V1 squared plus a half C2 V2 squared. That is the energy stored in this first original case. The total energy will be given by, if we substitute, a half times 2 times 10 to the negative 6 times 50 squared plus a half times 3 times 10 to the negative 6 times 100 squared. And I will not go to the next step. I will give you the final answer there. And that should be able to give you the total energy in the first case as 1.75. 1.75 times 10 to the negative, I think should be to the negative 6, the negative 2 times 10 to the negative 2. Now this is the energy before. Now part 2, if these capacitors are connected, they are emphasizing that they are connected with similar plates joined together, C1 and C2. That statement means that the capacitors are now connected in parallel. And if they are connected in the parallel, their effective capacitance is obtained by adding. So their C total will be C1 plus C2. And of course, that will give us 5 microfarads. Now when they are connected here, the PD, they are asking us to find the total charge. To find the total charge. Now, find the total charge when they are connected. The total charge here is the sum. But if they are connected here, the PD they get will be that. And from charge is equal to CV, the charge they have in the second case will be equal to our 5, which is the effective, times the PD here, times, of course, 10 to the negative 6. Now, what happens is the total charge before should be equal to the total charge after. The total charge before should be equivalent to the total charge after if they are connected. The condition here is the total charge in case 1 should be equal to the charge in B, in A above, this one here. Implying that the 100 plus 300 times the micro should be equal to the 5 times 10 to the negative 6 V. This will give us the PD across the arrangement. If we compute, we should be able to get to the PD by calculation as, because this will go as 80 volts. Because this is 400 divided by 5. So the PD, when they are put in this kind of arrangement, or that connection, will be equal to 80 volts. But they are telling us to find the total charge. And therefore, the total charge, we have already got it as 100 plus 300. Find the total charge. We can say the total charge for purposes of capturing is 300 plus 100 micro coulombs, which will be 400 microcoulombs. And then they are asking us also calculate the loss in energy. Now we got the energy here before. Now we need to get the energy. When they are connected here, the energy, the new energy, since the capacitance is now 5, the energy, which I will call final, will again be a half C T, I call it CT, times V squared. And now we have got the V there. So the final energy will be a half times the effective capacitance times the PD squared. That will be 6,400. And this final energy will be given by, if you compute, you should be able to get 1.6 times 10 to the negative 2 joules. That answers, we are moving towards part 3, where they're telling us to find the loss in energy. Notice that this is the energy before, which we can call the initial energy, and this is the final energy. So the loss in energy is obtained from our initial energy, which I called ET, minus the final energy. And the loss is therefore equal to 1.75 minus 1.6 times 10 to the negative 2. And when we subtract, we definitely get 0.15. 0.15. This is the loss in energy. The loss in energy is given by that value. Is given by that value. And finally, on that number, they want us to give a reason. They are asking us to comment on the loss in energy. They want us to comment, give a comment. I believe that as you capture this, I can summarize that number with a comment here, that for part 4, the loss in energy, we say, is due to dissipation of charge in the connecting wires. In other words, this difference in energy loss is wasted as heat. So the loss in energy is due to dissipation of, you can call it heat instead of charge. Dissipation of heat in the connecting wires. So it is lost in form of heat in the connecting wires. That energy is lost in form of heat in the connecting wires. My dear producer, I think you can go to the next question as we give learners 1 minute or so to capture that solution. Okay. Our lesson is moving quite fast, so quickly we can interpret that number. A 10 microfarad capacitor is charged from a 30 volt supply and then connected to an uncharged capacitor. And they want us to find the final PD on the combination. This number is like this, that if we connect, we have limited time, so I want to summarize this. If we connect that, we have seen the charge will be given by CV. So the charge is 30 times the capacitance, which is 10, times that. This charge, as we have seen from the previous example, is going to be equal to the same charge after connecting, if I call it C. After connecting that 10 to the 50, it implies that they are connected in parallel. So the effective will be 10 plus 6, 50 plus 10. And this is subjected to that times the PD. The charge that we will obtain in this position will be that times the PD. And I want us to find the PD. So these two expressions are equated. That 30 times 10 times 10 to the negative 6 is equal to 60 times 10 to the negative 6 V. That cancels, this 0 cancels, and then our V becomes 30 by 6, which is supposed to give us 5 volts. And then the second part, find the initial and final energy. Initial energy, 1 will be a half times 10 times 10 to the negative 6 times the PD, which is 30 squared, which is 900. You can compute that. And then the final energy would be a half times the effective. The final energy will be a half times the effective capacitance when they are connected, which is 60 times 10 to the negative 6 times the PD, which you have got squared. And that final energy, by calculation, should be able to give you the answer that you obtain there. 0.75. So this question here is summarized like that. My dear students, I want to summarize this lesson by reminding you that is as simple as that. It is a solution that is similar to the previous number. I want to summarize this lesson by reminding you that there are several questions. I think we have just left one number that was scheduled for this lesson. As an example that I have not done, the number which was supposed to come after this, I'm sure you took the the photos or the pictures or the screenshots. You now have enough information to work through, but when we meet for the next lesson, we may actually work through that particular number. You definitely have vast exercises. What I want to mention finally is that if you look at the last slide, my producer, give me the last slide, the very last slide. You notice that every year, 2011, 2012, 29, 28, 27, even the years I have skipped in between have a question on electrostatics. So this is a section where a very good candidate will actually find their two numbers. It is a must that there will be a number with a capacitor related question. There will be a number with electrostatics, electric field intensity, electric potential, and related questions every year. Use the question bank book and please keep practicing. Don't forget to visit my online page, Let's Learn From Home, for additional work. Have a good day. God bless you. Gachari Mabaga.
somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne.
She gives you her number, but your pen didn't work and the bus is gone. Get a pen you can rely on. Big Crystal, the long-lasting pen with perfect ink flow.
Wamune.
Green Hill Academy has high standards of learning and the teachers are very good. They give you a sense of belonging.
Green Hill has helped me to discover my talent.
The environment is good.
Encouraged us children to be excellent.
Wamune.
Combo University, a private chartered university that offers world-class education at all levels, including certificates, diplomas, bachelor's and master's degrees. Our courses include computing and IT, law, journalism, nursing, business administration, education, fashion and design, and many more. Admissions for the August 2020 intake are still open. Will you join us?
Wamune.
Kids Kingdom Kindergarten and Daycare. Somero ly'abaana bato. Omuzadde leeta omwana ogenda okola ebibyo. Ebyokuzanyisa by'abaana byonna mu nsi tubirina. Ate nga abaana we bazannyira wagazi nnyo. Jjukira security enka. Amasomero gonna gali mu kikomera. Abasomesa be tulina bakugu mu baana. Abaana tubaliisa bulungi nnyo munnange. Tulina main campus e Buddo Naggalabi. Nga bw'akayisa Buddo.
Fellow Ugandans, thank you for being patient and mindful of others during this very difficult lockdown due to the COVID-19. True, it's not easy for most people to stay at home the whole day for many weeks. While this stay-home period has been a restoration of many families, it has also been a daunting time for other families which are breaking up as a result. We are all living in times of great fear, panic, and anxiety. I know many are particularly fearful about what tomorrow may or may not bring. However, I encourage you to stay strong and not give in to these emotions. Remain steadfast, eyes on the prize. We all want to come out of this